Good afternoon. Thanks for being here after the lunch session. So I hope I would not make you drowsy. So I tried preparing this presentation so that it covers some basics about the graphics stack in Linux, how it is layered, and what components been involved. As part of the usual open source development from our end, I was been doing most of the works in the drivers, let's say for the custom requirement or upstream in Allwinner SoC or Rockchip SoC, specifically in display controllers, adding additional display panel supports and so on. But lately there have been interest from our custom requirements to handle things in Flutter and other user space applications, which is also new to us, to add support to components like embedder in Flutter to get it working with it. So as part of it, I thought of putting this presentation more generic in Linux graphics stack components from top down, and let's see how it goes. So shortly about myself, I've been doing embedded software development for maybe 12, 13 years in terms of Linux and Zephyr RTOS these days. And our primary focus is mostly in the embedded software, low-level driver developments and BSP supports. And I myself live in Berlin. I work for a company named Linumiz, and the company which does embedded software servicing in the field of Linux and Zephyr RTOS, as in we do software consulting and software developments mostly. And so to start off with something very simple, grayscale to understand in an easier way, I tried representing the older CRT displays and how it works. So in the left, for the simplicity reasons, I kept it like a 8-bit frame buffer, and the 8-bit frame buffer by itself doesn't represent the whole RGB pixel itself, but instead in an XY coordinate, if you think of it, it's like a stacked frame buffer planes, and out of which each frame buffer will have 8-bit value, that is like 0 to 255 to represent that particular pixel. And this is the way it is organized as like stacked plated planes. And in the right, you see the color map, which technically decodes or translates this into 24-bit RGB by indexing into the plates. And this 24-bit RGB will technically be emitted into the hardware display and infra, which would translate into a real voltage signal, let's say digital to analog signal, and that would translate into a voltage which would illuminate the electrode or electron beam into your cathode ray, and then that's what you see in the real pixel. So all the way from your pixel frame in the RAM, let's say for every byte, and then translating that into a 24-bit RGB, and then coming into a hardware layer and then displaying it. So this is like a kind of old school, or you can say 20, 30 years before time, how it worked. Right now, what we see in terms of the hardware links is more complex. For example, it's not simple digital to analog converter, which converts the digital signal, which means like 0 to 255 into a according voltage level. Instead, we have a complex systems like MIPI, LVDS, HDMI, and other systems. That's how we physically link it together. But also on the other side, the 8-bit frame is not more 8-bit frame. It's more of like one single pixel itself is representing the RGB together with the alpha blending. It's like 32-bit value, 4-bit for each pixel. And then it covers what is the depth of the pixel, brightness, resolutions, and so on. So it's more of complex in current scenario. But this would give you a rough overview of like how a bit plane translate into a real pixel value in the old school style. So coming back to how we have currently the Linux kernel graphics stack layered, starting with the application until the hardware layer. So usually we have this application stack wherein you have the Qt or Flutter or any form of toolkit where you develop the application on top of it, where you, let's say, try to draw a picture, probably a rectangle or triangle. And from there, that vectorized picture, how it translates back to the windowing system and rendering manager to translate into a 2D image or 3D image using Mesa 3D. And then the space between user space and kernel space basically hands off this thing. and the kernel space scans out this buffer into the real hardware. So when I say scans out, it's like a frame buffer memory which is prepared in the user space or prepared by the user space, and the kernel takes care of scans out into the display pipeline of the hardware itself. So that's the nutshell. So there are variations in terms of how it is done. When you have a GPU or when you do not have a GPU, the whole thing happens in CPU. And when you have a GPU, there are offloading engines which takes care of rendering or accelerating various things. So how it layered and what buffer it will be prepared and how this whole architecture will work in Linux graphics stack. If you, let's say, open a PNG file or a JPEG file from the application or simply draw a new image, how it renders into the display. I tried expanding each and every block of this layer in the following slides. And let's say starting with the AppKit, and then ending up with hardware. So a specific example from an Allwinner SoC series. So I will go stepwise and probably expand every new technical terms which is introduced in slides, like compositor. What is compositor? Let's say if I say plane, what exactly plane means in terms of software side and hardware side. So we go stepwise, and then I have slides to expand. Before expanding this application toolkit until hardware, I have some preparation slides in top, how this realistically look like in the start. So this is a whole architecture, but is this the same architecture against everything? Let's say if you do not have a GPU, how does CPU handles it? So if you have a GPU, but you wanted to render a video instead of an image or simple file, so you play a video, how does it basically renders into this real display and real scan out happens? So that's what we're going to see now. So in case of CPU, the application, which itself like Flutter or Qt, any application which you can imagine, or even simple PNG viewer or a file viewer, it basically rasterizes. When I say rasterize, the term means like it converts from the file which you have needs to be decoded, decompressed, and converted into a form where the CPU understands or the memory display controller understands. So the translation means like pixel format in a 2D vector. So from vector to the rasterized pixel form. So that is called rasterization. So in the CPU case, it is done in the rasterization done in the CPU, and wherein the next stage is basically Wayland's shared memory, which is again given to the compositor. The compositor could be X11 or Wayland itself. And the barrier from compositor to the next step is basically scan out happens in the kernel side from the DRM and then the display driver and then to the final panel itself. So we would expand eventually each and every portions of in following slides. But the most important portion which I wanted to emphasize in the first slide itself is like compositor is placed in all the following presentations. But if you can ask me like if the compositor is really mandatory for displaying something basic, I would say no. The application can directly speak with the Mesa 3D and do the rendering directly. For example, Flutter doesn't realistically require compositor all the time. So I would, for easy understanding or presentation, I put up compositor in all the following presentations. So in case of GPU, what we see is after the app being using the Mesa 3D's GLES or Vulkan implementation, which is from Khronos interfaces, which would eventually produce a DMA buffer compared to the previous one where I placed up the compositor buffer or the Wayland compositor shared memory buffer. In this case, it would produce a DMA buffer and give it to the compositor, and the rest is same. And rest is same by meaning there is an expansion like how it is done in the GPU case and how it is done without the GPU case. And then one last thing is about the video decoding portion. The video itself is like given in, let's say, a simple NV12 format and produced as like decoded with hardware decoder, or it's like CPU decoded and then given it with the compositor. But with this slide, I would conclude, like say, I will not speak about videos any further in the following slides, because for the simplicity understanding, more of things we will speak about in terms of displaying how a PNG file or a simple text editor you can open from an UI side, how it works. So first, before getting in that representation, I would like to say a few words about what would be in the memory, meaning RAM or the hardware memory, let's say planes, or how it is represented in planes. So Okay, maybe this picture is better in terms of speaking about it. What lives inside this memory itself? Let's say the pixel format, which we say X RGB, which is like X, wherein you can append alpha blending on top of it, wherein the XRGB portion. On the right, we represented like NV12, which is for the video format. So when it comes out to be the frame buffer, let's say when you create with a capacitor or any form of memory, you represent this to the DRM subsystem in the Linux kernel. This doesn't carry the pixel by itself. Instead, it would point to a memory which already contains the data of the display and with additional metadata. So frame buffer itself by only represents the metadata information, which contains format, stride, and most importantly, the modifier. So when I say modifier, so the plane, when I say hardware plane, it's the memory which is associated with the display controller and the hardware. When we fill in the planes, and that is the one which will be scanned out for the real display pipeline, and then what will be displayed in the panel in the end. So if the modifier supports the direct hardware display pipeline or the display controller itself, so there is a method called direct scan out, and I would represent that in the following slide. And if that modifier is not supported by the display controller, there has been an intermediate job which needs to do blending or additional translation done by the compositor to convert into an RGB before representing into the display panel or the display controller itself. So wherein the primary plane, which represents the RGB UI, which will translate this memory from the frame buffer, and then it would be scanned out and sent to this CRTC timing. So the remaining portions, let's say the kernel portion, we will see in the following slides, say how scan out works, what I meant by scan out in terms of buffering. So this is one simple, I have two representations here, one for the GPU accelerated path and one for the CPU only path. So when you do not have a GPU in your system or you do not have a functional software for the GPU, how does the rendering system works when it goes with CPU path only? So the application path, wherein the toolkit, for example, you can be a PNG viewer or a JPEG viewer, technically decodes using its own library. Let's call libpng or libjpeg library that would basically decode or decompress that particular file from the raw, a compressed form into a raw format, and then the CPU rasterizes with set of libraries called Cairo, or you can Cairo as an example. There could be additional libraries in the graphics to do it. So when I say rasterize, again, as I mentioned, it would convert that from a 2D vector into a form where the hardware understands, which is the raw pixel format, 2D vector format. So the application software and their library would take care of that, and that output would be a buffer, and that buffer would be hand off to the compositor. So the compositor would have additional jobs. For example, if you have 2 or 3 applications open in parallel, for example, a PNG viewer and a video player and let's say maybe a Thunderbird application, how does it render all of them together and what needs to go into the final plane? So there are plenty of things which would be done as part of compositor, which we discuss in like the compositor expansion, but the buffer which is prepared would be given to the compositor, and then it would be hand off to the KMS system, which is like the kernel portion of the DRM subsystem. So when it goes to the handoff to the kernel DRM subsystem, the display controller as part of your SoC or hardware will take care of scanning the hardware planes, which is prepared as a buffer, and give to the real display. For example, it could be my HDMI, which is as part of the projector here, or it could be LVDS or DSI planes, MIPI DSI planes to display it. So that is the path where CRTC decides the timing of that, or usually we call it timing controller in terms of hardware terminology. And the next step would be respective hardware. The simplified example would be LVDS. There would be an LVDS controller and an LVDS PHY, and then the data would be translated into a differential pair signal, and then that illuminates the display, which is like an LVDS panel, which could be 18-bit or 24-bit accordingly. So there could be additional pipelines like DSI, HDMI, which I would say. But one additional point here is the when we use CPU only rendering path, the let's say the CPU needs to have an additional buffer so that like when you move one image to another or a next image, it doesn't need to like tear down, meaning it is not the image which you see in the real display is not like half filled. It is all fully complete by having double buffering or more than double buffering or triple buffering, basically the compositor can do additional things. Let's say keep multiple buffers in pipeline for the next things to display, and then when you do a real commit, I mean when I say commit, it's a hard software terminology I'm making here on the KMS system, and then it would eventually render into the final plane. So when it renders, it is a complete one which would be seeing it. There is no like partial complete and partial tear down. So for which to happen in the CPU rendering path, you need to have like double buffering or triple buffering accordingly in the compositor system. So on the other scale, the same image, but with additional thing, one component which is called MESA 3D, which handles the acceleration portion. So the first one, wherein the image decoding portion can still be hardware done. It can be still CPU done. If you have a specific IP block which does the PNG decoding or JPEG decoding, that would basically decode that from the hardware side and give a buffer called DMA buffer directly. And MESA 3D, what it would do, basically imports this DMA buffer and it would do the, let's say, acceleration on behalf of it and then send to the compositor. So what differs from the previous one, in here we do the whole thing, rasterization, composition, everything in the CPU, whereas in this case, the MESA 3D implementation, which technically does the hardware acceleration using the buffer object. I mean, the graphic execution manager would take care of doing that with accelerating there, and then produce a buffer called DMA buffer. And then the DMA buffer is what handed over to the Wayland. So all the remaining path which we discussed in the kernel space remains same. And there is one technical difference. One is direct scan out, another one is the compositor path, which I mentioned there. So direct scan out is what we usually call when you have a hardware plane, the display controller having a hardware plane, and then the format of the image which comes from the, or the buffer which comes from the user space matches exactly the format and the modifier. The compositor can map the plane into the buffer object directly. This means there is no additional pass. Instead, the application can directly render into the plane, and then the plane would be scanned out into the real hardware. So when there is this modifier which doesn't support, then we need to have an additional pass in the compositor which translates into an RGB again, and then give it to the primary plane to display into the CRTC timing system. So that's one difference. So most of these embedded systems which we today have on Allwinner Rockchip primarily supports the direct scan out, which in this case, so technically renders directly the DMA buffer in this case, let's say accelerating the whole path of it. So that's one portion of path I expanded. From this point on, what we saw in the first slide, expanding the app toolkit until the hardware portion, I would gradually expand each slide, but not go super detailed for each and every instance of it. So the app toolkit by itself, I said Qt, GTK or STL, any form of application toolkit which you can imagine, Flutter, I mean, which would eventually help the application developer to create an image or 3D image, or the one which you see in a car infotainment systems to have a, let's say, tiled window widgets and so on. The application toolkit abstracts the APIs and helps the application developer to develop such toolkits and so on without knowing the back end of hardware, or even in fact without knowing the display controller, how it does it and so on. But there are additional things which we need to know. The backend needs to be chosen during the compile time or link time, or even for development purposes, you can specifically say you wanted to choose with compositor or without compositor, with GPU or without GPU acceleration path, and specifically. So there are various variables available for respect to application toolkits. I haven't put the Flutter here, I think. Yeah, I mostly put the Qt and other STL related rendering systems. So there are every application toolkit provides a set of global environment variable where you can provide that during compilation. That path would eventually decide whether it goes to the CPU rasterization path or the GPU accelerated path in this cycle. So that would eventually give to Wayland, and Wayland would again composite together and send it to the hardware KMS DRM system. So as I said in the first slide, Flutter can do, or any form of application toolkit can directly speak with the Mesa, and then Mesa can directly render these things into the real panel. So that doesn't need to be a compositor in place at all, but this is just a reference example. There could be multiple paths in terms of pipelines. So that's about the application toolkit which we spoke. And the second thing on the architectural hierarchy which we saw is the windowing system. So the windowing system by itself is, there are a couple of them available. What is the role? You can say, let's say, if you have multiple applications opened in your system and you wanted to overlap one another, let's say, for example, if I open a terminal on top of this, so if I open a terminal on top of this, how does it basically render this terminal in here? So wait, I just skipped there. So that's the role of composition system, to get inputs from multiple applications or get buffers from multiple applications and decide what goes to the final panel or final display system and what you see technically in the system, real display. So there are a couple of things available. One is X11, which is from very old days, and another one is Weston. And one prime difference which I always say is with X11, there is this X11 client which speaks with the display server, which is Xorg, and then the Xorg again composites based on multiple interfaces from multiple clients, and then the compositor decides into the KMS or DRM system to the low level. So with Wayland being directly supporting the DMA buffer handling it, and there is no additional hop of the server, the display server, and then the display client, the Wayland can do better in terms of one hop less to do the display. So predominantly in the embedded systems, that's why we see Wayland as an reference usage, because of the low latency thing implemented as part of it. So again, I tried representing this in a picture here. So as I said, left wherein the client would speak with the Xorg server, which is the display server, which again does the composition and sends it to the display engine. With the right, you can see the application toolkit directly speaks with the Wayland compositor because it's of DMA buffer which has been handled in the application toolkit. Let's say Linux DMA buffer as a reference, and then it can directly scan out into the real display itself. So that's one hop less in there. So that, I mean, once again, that's what verbally or textually represented in these two slides. And yeah, with application A, B, C, and creating multiple DMA buffers or buffers itself given to the compositor, and then the compositor decides what needs to be blend or what needs to be exactly decided. It decides how it needs to, how you wanted to realistically see the display. So which plane comes on top. For example, the shell which comes on top of my presentation, or another application lives on top of the other application. So that's the role of the compositor in there. And the next step is about the implementation of the graphics acceleration in the user space. I usually call, say, the graphics stack in Linux is split between user space and kernel space with equal responsibility. In kernel space, you say DRM subsystems and its counterpart implementation for DRM drivers, display controllers, and so on. But on the same side, there is also an implementation called Mesa 3D, a reference implementation of Khronos APIs. So it is OpenGL, OpenGL ES, Vulkan, and whatnot. All of these implementations are combined together with one software package called Mesa 3D, which would exposes the GL APIs or Vulkan APIs on top. The application needs to decide. Here, the application can be anything. It could be Flutter, it could be your Wayland compositor by itself or so. It needs to decide which path it needs to take, depends on the compilation system. And then based on which it will go into the same route of creating the buffer and giving it to the kernel space. So this would give you a better view about it. So the API fronts here is basically OpenGL and GL ES frontends or Vulkan ICD. When I say ICD, it's like client drivers for the respective hardwares. So GL is like more of a high-level stateless implementation, whereas with Vulkan you have this stateful or like low-level access towards how GPU works, how you directly access with Vulkan specifications, recent involvement. So when you do application development on top of with OpenGL or Vulkan on top, it basically translates this into a shader input, and then you have a shader compiler internally, and then it would translate to an intermediate language or intermediate representation, and then it finally drives into the respective hardware. When it comes to the OpenGL or GLES based accelerated hardwares in GPU, we call it as gallium, and there is in the other side you have Vulkan. So currently we've been working with the Imagination Rogue implementation for specific SoC on the ICDs. That's why I've been evolving with I've been exploring this path as well. So on the gallium front and then the Vulkan front, it's more of these days implementation is leaning towards or aligning towards Vulkan, but there is one additional layer called zinc in the Mesa 3D, which when the application can still invoke the OpenGL GLES APIs, but still can consume the Vulkan backend drivers or in the ICDs. So the zinc is the one which translates from OpenGL and GLES into the Vulkan wrapping. So here, as I with the GPU path or the acceleration path which I mentioned, there is one common thing which is called DMA buffer. The buffer which is handoff to the kernel to scan out to the let's say the real display panel. Either it's a hardware video decoder, or it could be a GPU rendering system, or a PNG decoder, or in fact video decoder in the camera subsystem. All of this would basically export a common thing called DMA FD. This doesn't have any physical or device like dev so and so in your device system, but it would expose a virtual FD, which would carry the metadata for the respective DMA buffers. Metadata inside the DMA buffer, and also pointing to the memory location where exactly your data lives for the display itself. So, and all of the low-level systems, which is Vulkan or Mesa 3D or Wayland composition, or in fact XL11, can directly import this DMA FD into their implementation or invoke this and directly consume this buffer and sends this to the kernel DRM system to scan it out. So this way, there is one thing which is big change, which is when you open a file, when you display something in graphics system, it is not like the memory which would be copied from every layer and layer and layer. So you can assume like a network subsystem socket buffer, where the Ethernet driver captures the data and sends to the upper surface for the application. The same escape buff will be the consumer. There is no additional copies from one layer to another. Something like that you can assume like DMA buffer, wherein handling from the display system from one layer to another. It is not the whole content of your display which would be copied from every instance of the stack. It is the same FD which will be sent from one layer to another. And then the DMA buffer finally lands into the KMS system. Maybe I would skip this slide because this might be a closer inspection of how an object pipeline of the graphics system would work. Yeah. So with respect to, so far we spoke about the user space being preparing this whole buffer, DMA buffer, or from composited buffer from an Wayland compositor or so. This would technically do a commit into the KMS or DRM system in the kernel side, where we have three different planes. One is the primary plane, which carries the RGB, which would eventually need to go to the display. And the second in the middle, which is where you have, let's say, a video pipeline where it can additionally overlay on top. And the leftmost is about the cursor plane. When you have an input device like mouse or keyboard, those needs to also come into this blending path. So all of them as like different planes, and overlay can be any number of overlay planes, because it depends on how complex your YUV or format of NV12 video systems would be. And then finally it would blend and given to the CRTC timing system. So when I say CRTC, which is basically the display controller which triggers the timing and then gives this output to the respective display path. So when I say display path, that's what I meant. So the CRTC or the display controller serializes the data to the LVDS, and then the LVDS will have its own PHY physical layer to send the data to the real physical layer, and it would be a differential signal driving the display itself. One additional which I can say is on the DSI, you have DSI host controller on your IP, and then there is like DSI panel controller, or in fact there are multiple additional bridges in place these days. For example, the data which is, what you have is an interface which is DSI or HDMI, but you have a translation which is called bridge from MIPI to HDMI or HDMI to MIPI and so on. So it's also part of this, which I haven't represented here, but that would have an additional staging in between, and then the bridge would eventually translate into the final buffer. Okay, then one final example which I wanted to show, which I worked on the Allwinner pipeline. So when it comes to the hardware pipeline, the display controller or the display which I mentioned there would register to the DRM core that it's itself as a display controller, and together with it comes as like display controller itself is represented as like a timing controller, under which how MIPI is connected with this or LVDS is connected with this, and what panel you're using. For example, it could be any panel from any of the companies which you produces it, and how it is connected and how your final display would arrive at. So this is the hardware representation, as in like you see in the schematics, let's say the display controller pipeline which is coming, where you have a MIPI display connected or LVDS display connected directly in the system. But how does the Linux kernel knows this information, so that like when you open up something from the user space, this is the path or traversal path it needs to choose. So that needs to be coming from the device tree of the Linux kernel. So in terms of device tree, in the top, that's the display controller which is represented. In here is like the timing controller, which comes with multiple ports, depends on the hardware capabilities. So in here it is an LCD output, or I can say in the next thing, MIPI controller by itself having multiple ports, saying it is having a output towards a specific panel. So during the initialization of the DRM subsystem, it would parse this whole device tree and creates the software pipeline equivalential to this hardware pipeline, starting with the display controller, the next is timing controller, and then following with the MIPI and so on. So equivalential to the hardware pipeline, there would be a software pipeline which would be prepared by the kernel based on the device tree input, and then you have the final panel which understands the MIPI DSI commands and data to represent this into the final display. So that's the input which you provide to the kernel, and then display basically works. So this is one final representation of what we spoke so far. Let's say I didn't want to take a sharp tail. It represents both the GPU path and as well as CPU path, and as well as, let's say, how your image basically works with the compositor and without a compositor in this case. So Wayland is there, but without Wayland, there is also a possibility where you can do directly to the KMS system, and then the Mesa can speak with it. So Mesa by itself, it directly interacts with the libdrm, which would basically handle the dev DRI device in the Linux kernel. And as we spoke on the direct scan-out or the GPU compositor or compositor-based path. Otherwise, the rest of the slides is most of details would be like to expand what we spoke in terms of terminologies, and then these all set of tools which you technically use or figure out when you are developing something called a display driver or a panel driver to figure out what is happening. Let's say, for example, GL Mark II, when you wanted to benchmark an OpenGL implementation of your Mesa driver or the GPU itself, then you would benchmark it with GL Mark II. Likewise, there is also Vulkan-based testings and so on. There are following slides where you basically help display something when you have each and every stage of your display. You don't need to have like a Flutter application starting with and developing your driver. Instead, you can just use some of these utilities and figure out a basic example how it works. Otherwise, there are simple environment variable which would consume or help you figure out respective Mesa implementation or application implementation to debug. One quick example is the ICD file name, which I gave there. So the Vulkan ICD file name is what helps the Mesa to understand, or the Mesa-based application to understand what the client driver needs to use. Let's say Imaginations or Panfrost or respective driver needs to use. That would contain a list of information, and then the application can decode it. And there are additional debug, whereas Mesa debug, these all would help you debug your development in the early stage of creating your display driver or GPU. So that's in a nutshell. And there are additional slides in the following, which I'm not going to explain. For example, the terminologies which we spoke so far, what is a plane, what is a frame buffer, and so on. And detailing each and every pieces in there. Yeah. Otherwise, in short, this is more of like a basic exploration about how Linux graphics stack works from top to bottom, and how you can implement a respective driver. Let's say if you're implementing a display driver, if you're implementing a panel driver, or maybe an application itself, how do you care which path you need to choose, CPU rasterized path or GPU rasterized path, and so on. Yeah, I think that's it from my side. If you have questions, we can speak now. Thank you. Any questions specifically? Yes, please.
The direct scan out, I guess this only works if the application is not sharing the screen with any other application, so it's a full screen application.
Yes, exactly. So this application needs to be full screen and must fit the exact size of the plane and width and height. In fact, if you play a video, it needs to have additional parameters which needs to match so that you can do the direct scan out. And if not, then it would go to the compositor respectively and translates into an RGB and then renders it. Yes, that's correct. Yes, please.
So how do you ensure direct scan out? Because if you do a Wayland commit surface and maybe like miss full screen, then it will just, you'll get the compositor in the way.
Yeah.
Always ensure it.
Yeah, the question is, to repeat for the audience, the question is whether the system currently runs, whether it uses a direct scan out or it is not able to do it direct scan out. You have a way to debug it. Let me show if I can find the command, or let's say, oh, sorry. I think I placed it. Oh, wait. I missed it. Sorry. So there is a interface in sysfs to expose or find a respective DMA buffer in your pipeline to see whether it is going against going with the direct scan out, or it's going to the composition system to do the RGB again. So there is debugfs and sysfs interfaces where you can find this. But the point is, well, the DMA buffer which we spoke in here, which is sharing against, wait a second. Yeah, no, wait, not here. Which one? Yeah, so the DMA buffer itself is like, let's say one specific application produces one DMA buffer and sends it to the respective KMS system, which can be capable of doing direct scan out. But the next immediate DMA buffer, which is coming from another application or whatsoever, cannot be capable of the modifier, or as he mentioned about it is not full screen or so, then that needs to go into the composition system. So that is dynamically decided. But with respect to one specific application, when you are developing something, you can be sure that like if you follow that path, then it would eventually fit the screen configurations for the KMS. That would work. Otherwise, no. Yes, go on.
The VBank that happens, like say I've got a camera pipeline, I've got my camera streaming up to userspace, and I want the buffer to then go back to the display. Is there a way I can trace that, how long that will take in terms of when my VBank event happens and my display is, or my images onto the display?
In terms of timing, you mean?
Yeah.
Okay, so the question is again, when you do a video capture and display this into the display system, I repeat the question, so, or opening an image from your file system, and how much time it takes care to display into the final thing. I do not know if there is a tracing mechanism, maybe with camera for, I don't know. I'm not entirely sure how to trace it, but there are.
The buffer just want to display it on the screen, so how long does it take to go through the pipeline and the display stack?
The timing calculation, I'm not entirely sure if there is a way to f-trace this, or trace CMD might probably help in figuring out. I mean, I'm not sure if I represented those commands here. Let me see.
I guess if you're doing direct scan outs, you would talk directly to the hardware, right? But otherwise, you would go through the compositor, which might also have buffering.
Yeah, there is like a couple of commands which you can technically invoke. One is trace CMD and build this and figure out how long it would take in the path, or maybe ftrace would help in terms of figuring out how much amount of time and then find it in the debugfs. But I'm not entirely sure if there is a direct command or utility to figure this from the Linux DRM system. Yeah. Any other questions? Guess not. Thanks so much for your attention. Thanks for your time.